Good morning. In the last lecture, we were looking at conservation equations that we are required to, or we need to solve for, coming up with some idea of how convection heat transfer comes into play. And I also discussed alongside convection heat transfer, I was discussing that mass transfer is has a strong analogy with heat transfer. So I will take that thing forward today, and we'll discuss this analogy in more detail. And the idea of doing this, talking about this analogy, comes from the very fact that if you remember the equations that I had written in the last lecture, the governing equations, the energy equation and the concentration, or rather the species conservation equation, you would have noticed that the equations were very similar. They were governed by, or these dimensionless equations had a similar form where the non-dimensional coefficients could be replaced. So you could actually replace Prandtl by Schmidt and still get the same equation, and replace the temperature by concentration, and the equation will remain the same. So, and moreover, what I didn't prove, but I said in the last class, is that if you check the boundary conditions, they are also the same. So clearly, these two, the mathematics says that these two concepts are analogous. Okay. Now, uh, since the mathematical form of the equation is the same, the boundary layer temperature and concentration profile. So delta, if you want to write T star profile and delta and Ca star profiles in the boundary layer, would also be similar because the equations are similar. So what it means is that if you remember, I mentioned that the non-dimensional temperature was written in terms of a function f3. So I said f3, which was a function of x star, y star, the Reynolds number, Prandtl number, and dp star dx star. So this was the non-dimensional temperature. I'm now saying that this should also be similar to the non-dimensional concentration, which is C star, which was F, I think 6, yeah, F6, X star, Y star, again REL, but now we had Schmidt and dp star dx star. So the functional form of these two functions, f3 and f6, must be, or they should have the same functional form, if I can say this. Okay. Similarly, if T star and C star have the same functional form, clearly their derivatives at the wall would also have the same functional form, which means that F4, which was X star REL Prandtl for a given geometry, where I said for a given geometry dp star dx star is known from the free stream solution, so I'm not going to write that again. So F4 should also be same or similar to F7 X star REL and Schmidt. F4 was proportional to the velocity gradient, the non-dimensional velocity gradient, and so it was proportional to, or rather, not non-dimensional velocity gradient, but non-dimensional temperature gradient. So F4 was actually like, if I can say it here, F4 was like Nusselt number, and F7 was like the Sherwood number. So their functional forms should also be similar. And finally, if you go take it one step forward by saying that the functional forms are similar, so if I average over the length of the plate, so if I calculate average heat Nusselt number and average Sherwood number, that would mean that F5, which was only a function of now REL and Prandtl, should be similar to F8, REL, and Schmidt. That is the average Nusselt and the average Sherwood number. So the reason I'm saying these is that in general, we will see that the kind of mathematics we use to do these kinds of calculations, these, if we have one function, let's say if we have the function for, or if we know something about the functional form of dependence of Nusselt on Reynolds number and Prandtl number, we will use a similar behavior or the same equation but replace Prandtl by Schmidt and be able to derive the mass transfer coefficient for the mass transfer problem. But even without doing any experiments or doing any detailed calculations, we can still go ahead and do this. So the processes are interchangeable. Okay, the physics remains the same in both the processes because of the way the equations are written and the way the boundary conditions come out to be in the non-dimensional form. Now, as you will see very soon, by maybe the end of this lecture, you will see that Nusselt number could be written in. So we said Nusselt number is something like f4 of x star rel Prandtl. We will see that Nusselt number will come out to be some f4 prime, where prime doesn't mean derivative but a new function of x star rel into Prandtl to the power 1/3. Actually, I should say Prandtl to the power n, where n becomes 1 by 3. And similarly, you'll also see that Sherwood number would come out to be like f7 prime. So f7 prime is basically f7, but f7 in which Schmidt has been pulled out. So x star rel Schmidt to the power n. In both cases, n is a positive exponent, and frequently n is taken to be 1 by 3. I should say n is greater than 0, less than 1. It is not just any exponent, but a very specific exponent. So since this is something that I have yet to prove, or rather yet to show you, but let's say that we will see this very soon now, that Nusselt and Sherwood, we could write them in this form. It is now clear that since we said Nusselt and Sherwood are of the same form, and we now see that the only difference that they had was in the role of the non-dimensional number Prandtl or Schmidt number, right? PR or SC. It is, I hope it is clear, you can see this now, that the similarity, which I can write now as Nusselt by Prandtl to the power n, which was f4 prime x star rel, that would be the same as f7 prime x star rel, which is Sherwood number by Schmidt to the power n. Basically, I'm saying mathematically, since the forms are the same, and Prandtl and Schmidt have been somehow dissociated from the main function, then these remaining functions, f4 prime and f7 prime, should be the same functions. They cannot be two different functions. Okay, because transport in both processes, in both heat transfer and mass transfer, is being governed by its same equations and same boundary conditions. Now, this is actually a very powerful result, what I've written here. What this does is, if you just put the value of the Nusselt number can be written in terms of the heat transfer coefficient, and the Sherwood number can be written in terms of the mass transfer coefficient. So if I just plug those values in, and again, this is also true for, this is not just true for local values, but this kind of similarity will also be true for averaged parameters, for nu bar or sh bar. So let me say HL by K by Prandtl to the power n would be the same as HM L by, in this case, DAB. Remember, binary diffusion coefficient by Schmidt to the power n. And so I can write the ratio of H by HM as K by DAB into Lewis to the power n. And I defined Lewis number in the last class, which was the ratio of the Prandtl to the Schmidt number, I think, if I wrote, or Schmidt to the Prandtl number. So Lewis number comes in there, and then we can take it, or you can work this out for yourself, multiply up denominator and numerator by rho Cp. So if you do that, you can actually prove that this comes out to be rho Cp Lewis times 1 minus n, where n is 1 by 3, as I said. N is that exponent on the Prandtl and Schmidt number. So this kind of an equation can be very helpful if you have measurements or correlation for one, let's say, coefficient. It could be heat transfer coefficient that you have, and from that you can recover the mass transfer coefficient, or it could be the mass transfer coefficient that you somehow measure, and then you can recover the heat transfer coefficient. Okay, there is an application of this that we are going to discuss now, on how this kind of a result can be very helpful if you are trying to do some just trying to solve a problem where both heat and mass transfer are taking place. Okay, so and the problem relates to an application that you have seen, you must have seen. I mean, growing up, you would have seen this application in many places. But I will show you a very simple form and a canonical form of this application. So, say we have a pool of liquid. Okay, so we have, let's say, on a surface we have some liquid level. So the liquid is, let's say, some species A, and around this liquid there is a gas which is flowing over this liquid. So the gas temperature is T infinity. Okay, so think about this way, that you have A is maybe water, and gas is maybe air, which is flowing over this water surface. And specifically, what we are dealing with is an example of evaporative cooling. So evaporative cooling is very commonly encountered if you have seen these desert coolers, right, where you have this water falling through a surface or through a pad, which basically enhances the time it takes, or the contact time between air and water. Okay, and it also allows you to have that porous structure, so that more and more air can come in contact with water. So this is, or even a simple case would be an earthen pot. So an earthen pot is also something similar, that you have this water that goes through the pores of the pot. It emerges on the surface, and the surface is surrounded by air, and so then you have evaporator cooling, and that's how the liquid inside that earthen pot cools down. So say that we have this gas flowing over this surface. Now, what typically happens is that, as I was saying, that you have this evaporation of liquid on the surface, which may be at some temperature Ts, which I don't know yet. But the liquid evaporates because evaporation requires the liquid to have that latent change, or that this latent heat to be provided from somewhere. So the liquid basically evaporates, and consequently that energy comes out from the liquid itself. So the rest of the liquid basically cools down. So there is a cooling effect that is typically encountered in this case, because the liquid evaporates and it takes away the vapor. Basically is has a higher enthalpy, so it takes away that amount of energy with it. But now, if I'm looking at a steady state problem, now the liquid cannot just indefinitely cool. So it's not like that water will become ice one day, right? There has to be a sweet spot. So the sweet spot is dictated by the steady state. That at steady state, what should happen is that the rate of evaporation, or the rate at which heat is lost in the form of evaporation. So if I write this as Q double dash evaporation, the rate at which this energy is lost by evaporation, that must come from somewhere. If the same amount of energy doesn't come from somewhere, then the liquid will either cool, it actually keep cooling itself. So you can apply the energy equation if you think of it this way, that if E dot in and E dot out are not equal, and let's say there is no generation term, it's just a water layer on a surface. If E dot in is not equal to E dot out, then definitely there would be some E dot storage, right? So there would be some change in the internal energy of the fluid. But at steady state, you have E dot in going to be equal to E dot out. So that energy must come from somewhere, and that basically comes from this convection mode of transfer. So the gas is flowing over the surface, so it must be supplying some convection or some energy in the form of convection. So that energy intake must equal, or that rate of heat transfer must equal the rate at which evaporation takes place from the surface. And at that point, when this starts taking place, the surface temperature will actually become a constant, or it will basically achieve its steady state. Okay, so let's say that we are dealing with a scenario where there is no heat addition. So Q double dash, I'm saying Q double dash evaporation should be equal to Q double dash convection, and Q double dash evaporation would be given in terms of the mass flux, which I'm going to write as N double dash A. Small n denotes the mass flux, not the molar flux. So N double dash A into the latent heat into HFG. Right, that must be the amount of energy that is required to evaporate this liquid into vapor phase. But Q double dash convection would be the heat transfer coefficient H into T infinity minus Ts, where Ts is the surface temperature. Now, what is N double dash A? So let me write this equation again. So H T infinity minus Ts would be HFG. N double dash A can be written in terms of the mass transfer flux. We'll have HM times rho A at the saturation condition corresponding to Ts minus rho A infinity, which is basically the free stream density, or the density of the species A in the free stream, which is a gas. So if you're working with air, for instance, that would be it would be dictated by the specific humidity in the free stream. Okay, now we can just rearrange this equation. And the purpose of doing this analysis is to typically calculate what is the cooling effect. What is T infinity minus Ts? This is called as a cooling effect. How much temperature depression do we see at steady state? So we can write T infinity minus Ts to be HFG HM by H rho A saturation at Ts minus rho A infinity. Now H by HM I'm going to now use from the heat and mass transfer analogy, okay, in terms of Lewis number. So I'm going to write this as and also what I'll use is I'll also say that in this case, because typically at low pressures all gases behave similar to an ideal gas. So what I will do is I will replace, or I will invoke, ideal gas relationships and replace density by pressure. So we'll have T infinity minus Ts to be given as HFG into the molecular weight of the species A by the universal gas constant rho Cp Lewis to the power 2/3, and then we'll have Pa saturation at Ts by Ts minus Pa infinity by T infinity. So Pa infinity then becomes the partial pressure of A in the gas stream. So this equation, which is actually which has both, which has this unknown Ta infinity, or rather T infinity is known, which has this unknown Ts appearing on both sides, can be solved using a quadratic form. So you can set up the quadratic equation then and try and calculate what Ts should be, and then calculate what is the cooling effect for this system. Now there is one catch here that I have to mention. The catch is that these properties that we have used, especially rho, Cp, and even the Lewis number, you need to know, this, since the fluid, or since the problem has a variable temperature, there is Ts on the surface, there is T infinity coming in, and so these are properties of the gas phase, of the gas side. Okay, so you need to see which temperature should be taken. Typically, the temperature which is taken is the arithmetic mean of the two temperatures. So typically, you take the properties at T infinity plus Ts by 2. Okay, the mean temperature, if I can say. So once, because otherwise, if you assume it at T infinity, then you know that the gas is also in touch with a surface which is at Ts. So locally, it is also coming in, it has properties corresponding to Ts. So across the boundary layer, we are now saying that we take the approximate temperature, which is the mean temperature, to be able to do this analysis. Okay. So this is one way of invoking this uh, heat and mass transfer analogy. Let me also do a next item on this analogy, which is even more interesting. And this comes from what is called as a Reynolds analogy.
Sir,
Yeah,
sir, in the previous relation, if TS is unknown, then how
hmm.
do we take the properties?
Very good. Because you're saying that TS is unknown, then you do not know what these values will be, and so itself, you would not know what should be the. I mean, how do you even calculate this? So typically, what is done in this case again is that you will have to assume some value of Ts. So assume a value of Ts, calculate the arithmetic mean, put in those values here. So sort of, you're sort of guessing what Ts would be. Using that guess value, calculate these values, calculate Ts from this equation, and see that is it close to your guess or not. If it is not, then you have to maybe use that equation, the new value of Ts, again calculate arithmetic mean temperature, put in here, and then see whether it gets close. So you sort of end up doing some kind of a, if I can be a little loose in my nomenclature, but you end up doing some kind of Newton-Raphson method. You sort of guess, calculate, see how the guess works out, and then maybe if needed, recalculate until the difference becomes very small. So the guess value and the predicted value, if the difference becomes very small, then you can stop there. Okay.
Yes, sir.
Yeah. But I won't give you the trouble of that. Don't worry about this. If ever if I ever ask this question, I would not ask you to do iterations or try keep working this out. I will give you some hints, or something would be there if it comes to this. But yeah, but mathematically, this is what you will have to do. You can if you're doing it in practice. Let's say you're doing solving this problem for some, maybe you end up working on a problem of this kind after you graduate. The idea would be to sort of do this numerically. Then you would have to write a code to sort of solve this equation using one of the preferred iterative techniques. So most of these calculations are never done by hand, except at the undergraduate level, where we sort of rely on hand calculations. Industry doesn't work with hand calculations. Now, going to the Reynolds analogy. Now, what we will do is, so I spoke so much so far. I've spoken about analogy between heat and mass transfer. Now, I will talk about some more analogies, and this time analogies of momentum transfer, heat transfer, and mass transfer all together. And that is very interesting. So if you remember the governing equations, and if I suggest you look them up, or maybe I can just pull them out from the lecture notes from the last class. So we wrote these equations here. If you can see this, the three equations are here, the governing equations are there. In case, let me say, if dp star dx star was 0 and Prandtl number and Schmidt number were both equal to 1, then you can see that the three equations are pretty much the same equations. They have the same form, exact same form, and then the boundary conditions also the same way, or the same form, because the boundary conditions anyway do not depend on dp star dx star. So knowing this, I can say that if dp star dx star was 0 and Prandtl and Schmidt were both equal to 1, then you have the conservation equations of the same form. And the conservation equations are of the same form. In fact, I should also say conservation equations and boundary conditions, because boundary conditions are also important. So What it means is that the solutions for the non-dimensional velocity profile u star and t star and c star, these solutions must be equivalent because they have the same exact terms in all three equations, which means f1 should be the same as f3, which should be the same as f7 or f6. These three solutions will actually be the same functional forms. And more importantly, the derivatives now, du star dy star at y0, dt star dy star at y star 0, and dca star dy star at y star equal to 0 will also be the same, which means f2 would be the same as f4, which would be the same as f7. Now note that f2 was related to the skin friction coefficient, f4 was related to the Nusselt number, and f7 was related to the Sherwood number. And I'm saying related, I'm not saying they're equal because there's a subtle difference. The subtle difference is, if I again go back to the lecture, to the previous lecture, you see that f2 here, f2 actually goes as cf into rel by 2, right? f2 is actually cf into rel by 2. What is f4? uh, Sorry, not f4, yeah, f4, yeah, f4, where rpr is 1, Prandtl number is 1, f4 is just the same as Nusselt, right? And similarly f6, around f6, now f7, did I not write f7 somewhere? Oh yeah, there it is. f7 is the same as Sherwood number. So what this means is that by using this equation now, I can say cf into rel by 2 will be the same as Nusselt number, which would be the same as Sherwood number. And this is what is called as a Reynolds analogy. Let me say equation 1. This is the Reynolds analogy, which is of course applicable for a very, very special set of conditions. The special set of conditions are that the pressure gradient is 0 and the Prandtl and Schmidt number are equal to 1. Now, what is done typically, the Reynolds analogy is not written in this way, it's written in a slightly modified way. I have written a way which is easy to understand, I would say. But to write the Reynolds analogy in a more general way, two new non-dimensional numbers are defined. So the first number is called as a Stanton number, which is St, and then the other number is a mass transfer Stanton number, which is St with subscript m. So Stanton number is h by rho v cp, where v is a velocity, not volume. Please keep that in mind, which I can write in terms of Nusselt number and Reynolds number and Prandtl number. And the mass transfer Stanton number is just hm by v, which could be written as the Sherwood number by Reynolds number and Schmidt number. Okay, these are the definitions of these two numbers. So what I'm going to just do is now convert this equation, or rather substitute Nusselt number in terms of Stanton number, and Sherwood number again in terms of the mass transfer Stanton number. So we can say Cf into REL by 2 would be Stanton number, Reynolds number into Prandtl number, which would be the same as Stanton number for mass transfer into Reynolds number into Schmidt number. Now in our problem we said Prandtl number is 1, Schmidt number is 1, and Reynolds number can be cancelled. So we get Cf by 2 to be Stanton number, which is the same as a mass transfer Stanton number. So this is what you will see as a Reynolds analogy in maybe your textbook. I defined the easier way earlier, but I'm just now coming up with the more, let me just, yeah, the easier way was defined earlier, but I'm now just defining the more general way in which the Reynolds analogy is written. So what it means is, again, if I have, for this special case where the pressure gradient is zero and the Schmidt number and the Prandtl number are equal to 1, if I have data for skin friction coefficient, I can actually recover the Nusselt number and the Sherwood number by using this definition of the Stanton and the mass transfer Stanton number. So I don't need to repeat experiments. I don't need to do any more simulations. Just doing one set of experiments is enough to be able to determine everything about that situation, that scenario, or that geometry with those complications. Okay, but of course, as I said, there's a catch. The catch is that this is very, very special. You have to have Prandtl number to be equal to 1, you have to have Schmidt number equal to 1, and you have to have pressure gradient equal to 0. So its applicability to other scenarios, in fact more complex scenarios, is questionable. So what is done is that a new analogy was proposed. This is what is called as a modified Reynolds, or sometimes credited to the two gentlemen who actually came up with this analogy. So this is also called as a Chilton-Colburn analogy. So the modified Reynolds or Chilton-Colburn analogy basically improves upon this Reynolds analogy, and it improves by adding a few corrections to this analogy. So it becomes applicable to a range of other conditions. So to generalize, what they did was they said if CF by 2 could be written as Stanton times Prandtl to the power 2/3, which they wrote as the J factor for heat transfer. So this is called as JH is called as a Colburn J factor for heat transfer, and this is applicable. They found this kind of an analogy is applicable for a range of Prandtl. So it goes from 0.6 to 60 now. Instead of just Prandtl to be 1, they could make it applicable for a range now, a large range of Prandtl numbers. And for the mass transfer problem, they did a similar thing. They said CF by 2 could be written as the mass transfer Stanton number times Schmidt to the power 2/3, which was called as Jm, which is the J factor for mass transfer, and which is applicable for Schmidt with a slightly bigger range now, 3000 to 0.6. So by proposing these new analogies, what they said is that if you have data now for a given, let's say for the hydrodynamic condition, then you can recover the corresponding data for mass transfer problem or for heat transfer problem using just this simple equation. Now, it looks simple, but of course it has a big, there's a lot, and we will also use this further now as I go into the next segment. I will use this analogy in quite a few number of places. But it looks simple, but then there is still one issue which where this or which an issue that pertains or that persists with this choice of this analogy. So even though this is quite readily applicable for turbulent flows, this is quite it remains approximately valid for turbulent flows, even when dp star dx star may not be zero. Even when the pressure gradient may not be zero, we can still apply this uh, analogy for turbulent flows, and the reason there being that there is higher mixing, and so pressure gradient actually anyways has not such a large role in turbulent mixing or in turbulent transport. But in laminar flows, for laminar flows, this analogy can only be applied when dp star dx star is a very, very small number. So I would say nearly approximately zero. So laminar flows still have trouble reconciling this analogy, but turbulent flows have been shown to give approximate or good answers with this analogy. Now, thankfully for us, most flows that we deal with in nature are actually turbulent. Laminar flows are a notion which are rarely present in nature around us. Okay, so we will use these j factors quite frequently, and using these, a lot of our calculations would actually be simplified, as you will see that in the time to come. Now, there is one thing that I have not covered, and I would request you to please look at it. There is a section on, I think it's called section 6.9 in the book, but I have an older edition. Maybe you have a newer one, which may not be section 6.9, but it is called the effects of turbulence. And this is some background information on turbulence and how turbulence leads to higher mixing in the boundary layer. So I'm not covering that for a reason that it has to cover that, it would require me to maybe dig up a lot more information, and I could not condense that into a few minutes, and I think that would not have done justice to it either. So I'm leaving that to you. Read about it. If you're not able to follow it, it's okay. I think it is not everybody's cup of tea, but if you have some notional background of turbulence, if you looked at turbulence in some introductory way in the course on fluid mechanics, then this should make sense. What is being said about turbulence and how transport is enhanced in turbulent boundary layer would actually make sense when you read this section. Okay, so it's a very descriptive section with very, I think, hardly 2 3 equations in there, but hopefully it would make some sense, and you will understand why turbulent flows are beneficial if you're looking at heat and mass transfer. Okay, so we move to the next topic now, which is application of convection. But now we will look at so far we've only set up the background for convection. What happens in convection. I sort of discussed a little bit of the mathematics and some physics of the problem, that why transport happens and what are the important parameters that you will have to work with in heat and mass transfer calculations, especially convection type. Yeah. So we will now talk about convection as a broad category, and there are two or the category can be divided into two sections broadly. One is an external flow, and the second category is internal flow. Now, external flow is a we will call any flow as external flow if the boundary layer that forms on a surface, if it can develop freely without any constraints. So this will be a scenario where boundary layer can develop or develops without, or rather I should not say without, but let's say freely, develops freely without any constraints. So if it's like flow over a flat plate, right? If you have a flat plate and the plate is infinitely long, then the boundary layer will keep growing. It will not stop. It will not say that I've reached such a that it has reached maybe such a certain value that it should stop. It would not stop. The boundary layer will keep and keep growing. So external flows will typically be dealt with, or the kind of flows that we will deal with would be, for example, flow over a flat plate. We will have flow over certain obstacles. So obstacles typically that we will deal with would be cylinder or sphere, or even flow over airfoils. All these will fall under the category of external flows. Internal flows are different. In internal flow, the boundary layer cannot develop, in a free manner. So it eventually gets constrained, and I will show you what I mean by that in the next, maybe the next lecture. So it gets constrained that it cannot grow beyond a certain point. And the example of this that we will consider in this segment would be flow within a channel or a pipe. Some problems that you have maybe done in fluid mechanics as well, when you might have derived velocity profiles of flow within, a constrained geometry. So the primary reason why we are doing this now, this analysis in this form, is to be able to derive or to be able to determine convection coefficients for different geometries. Now, as I said, that geometry has a major role, even though the equations do not show that. But you know that dp star dx star comes from the geometry. So the geometry will actually influence what would be the convection coefficient for that given scenario. So there are two approaches to get these heat transfer coefficients. Okay, two approaches that I use in practice. One approach that we will very heavily rely on is the experimental approach, and this is also sometimes called as the empirical approach. So the experimental approach basically sort of deals with that. You set up an experiment, you perform an experiment on a given geometry under different conditions which are controlled in the laboratory, and get from the data that you get, you can sort of identify some correlations in terms of non-dimensional numbers. So we will discuss this, how this experimental approach works. But it basically works in the from a laboratory standpoint, that you have a geometry, you do experiments, get data, and maybe do some kind of curve fitting, if I can say it loosely. The other approach is theoretical, which I'm not going to be following in this case. In fact, in very rarely is it followed nowadays in convection heat transfer. But theoretical would mean that you either come up with an analytical solution to the problem, so you solve the governing equation somehow, or you develop numerical solutions. So basically, you solve the governing equation on a computer, so you solve it digitally. So these will be the two approaches that are typically, there out there to be able to come up with these calculations for heat transfer coefficients. Now, as I said, we will rely heavily on the empirical approach or the experimental approach. So let me give you an example of what the empirical approach will be. And we will choose a very simple case, uh, which is, say, flow over a flat plate. So say we have a flat plate of maybe some length L. There is a blower system by which I can, bring in some fluid at some velocity and some temperature and make it pass over this surface. What I can also do is, I can, to create a heat transfer problem, I can embed a heater inside this plate by putting a slot and passing current through this heater. So we have a voltage E and a current I that passes through this heater, and also make sure that heat transfer is only in one direction, so I can insulate the bottom surface of this plate, or rather all sides except one. I can insulate that side. So I know that the heat transfer will only be in one direction. That would be because of convection, as the fluid passes over this, bulk flow passes over this plate. So the surface temperature, if it's Ts and the area is maybe As, I can put thermocouples on the surface, measure Ts. I can also measure T infinity. by maybe controlling my own condition. I know that air is at a certain temperature, so I'm passing that, so I can measure that temperature as well. So Ts can be known, T infinity can be known, and so I know that Q double dash convection, which would be H, which is the heat transfer coefficient, let's say the average one, times As, Ts minus T infinity, this should be equal to E into I, the amount of heat dissipated by the electric heater at steady state, by the way, I should say, at steady state. So knowing everything else, I can figure out, or I can get some data for the heat transfer coefficient H bar L for this let's say one experiment. Now this experiment, let's say we were doing with air, I can repeat the same experiment with water or some other fluid which is conveniently available. So for I can do this for fluids, and as I'm saying, when the fluid changes, for instance, if I choose air, air has a Prandtl, I said, is about zero point 0.7, but if you choose water, the Prandtl number increases. So you can actually do this experiment for a range of fluids, and so you have data for each and every fluid. Moreover, you can change the velocity u infinity. Maybe you can change the, if there's a blower or a pump, you can change that pumping rate or the blowing rate, and that would also give you a bunch of data. For each of every u infinity, you'll get some data. You can change the length of the plate if that's possible. Change the length of the plate and get more data. So you can keep creating more and more data in this problem by this simple experiment. So what this will do is, if I have all this data available with me, I can have many different values of Nusselt number of Nu for a variety of Reynolds number and Prandtl number. So Nusselt number will come from the heat transfer coefficient. Reynolds number and Prandtl number, as I said, Prandtl number will come from the choice of the fluid, and Reynolds number also changes when you change the fluid, by the way, because the viscosity changes. But you can also change it by changing the length or the flow rate over the surface. So once you have this data, typically what is very often done is that you plot this data on a on an XY plot, where we can have log of the Nusselt number, Nusselt number, let's say bar, which is the average Nusselt number, versus log of the Reynolds number. So on a log scale, we can plot this data, and we will do it for different Prandtl number. So let's say for one Prandtl number, we have some data which comes out like that. So let's say this is PR1. For a second Prandtl number, maybe you have some other data, which is Prandtl number 2. And maybe for a third one, there is some more data that we have, and you fit a curve through it. So what is often done is that when you have this kind of data, often you will see that we can write Nusselt number in the following way. We can write it in the terms of Reynolds number and Prandtl number, by saying that it is some constant times Reynolds number to the power m and Prandtl number to the power n, where C, m, and n are constants which depend on flow conditions and nature of geometry. Okay, but that is the whole idea, that if we do this experiment enough number of times, we should be able to generate this kind of a curve fit, and that is what I call a correlation. In fact, I've been saying correlation, but this is a typical correlation that we will be dealing with, that we can get for a range of conditions, or for a given, if you do this experiment on a given geometry, we can get this kind of correlation, and then from there we can obtain predictions for conditions and at which we may not have done any experiments. So similar to this kind of information again, or I mean, it's a as I was saying, that if we establish heat and mass transfer analogy, if I can write Nusselt number in this form, I can also write Sherwood number in the same form. So I can also write, if mass transfer, heat and mass transfer analogy was valid, so if heat as mass and mass transfer analogy is valid, then I can also write Sherwood number as C RU to the power m times Schmidt to the power n. So that is needless to say that we don't need to do the same thing for mass transfer now. So that is a typical approach that is used to calculate the heat transfer coefficient in the empirical method. Now, thankfully for us, most of these experiments are already done for most common geometries. If you have a new geometry altogether, you may have to go and do this experiment in the lab and establish your own data. But most of this data is already available, and it's available in the form of such correlations that I was saying. So what we will do in this part of this course is to try and look at, if we are solving a problem of heat transfer by convection, we can pick out an appropriate correlation, use use calculate Reynolds number and Prandtl number for our choice of the fluid and the condition, and then use that correlation to calculate Nusselt number, and from the Nusselt number calculate the heat transfer coefficient. Okay. The only catch here would be that when you calculate these properties for Nusselt and or rather Reynolds number and Prandtl number, and even the Nusselt number, because the Nusselt number will have the thermal conductivity of the fluid, the properties are calculated at what is called as film temperature. The film temperature TF is the surface temperature plus the free stream temperature by 2. So the arithmetic mean temperature. And again, that is to ensure that we have at least some accuracy. If you calculate it only at one temperature, then you know that near the surface, for example, if you calculate properties at T infinity, near the surface, the predictions will actually fail because the temperature might be very high, and so the properties can actually change quite significantly when you go near the surface, and vice versa. Okay, so this will be our approach. So to give you some idea of how we even come up with this kind of an equation, to give you some idea of how we even came up with this equation, okay, let me take an example, and I will try and refrain from detailed mathematics. I will actually, rather, my plan was to do this mathematically to prove you why this comes out like this, but I feel that it will be a waste of time, and it would also be, it can be boring for some people who are not fans of calculus. So what I'm going to do is I'm going to upload the details of the mathematics separately. You can read it. Some of you who may be interested can read it. It is not for evaluation purposes, so it is completely by your choice. If you want to read and understand how this is derived, but I will try and at least give you some flavor of it in the lecture today. And the problem that I'm going to deal with again is the flat plate problem. And in this problem, how we reach some semblance of a correlation of this type is what I'm going to try and establish. So the flat plate problem, and we will only look at the hydrodynamics of it for now. Say we are dealing with the flat plate, which has a length L. Okay, and the length L is such that the flow that develops over this plate remains laminar for some distance, and maybe then it becomes turbulent. So you have very neat streamlines up to a certain point, but beyond that you get turbulent mixing or wake vortices that are formed. So there is transition. So what we will try and do is to follow the path that was derived, or the follow the method that was derived by Blasius for the boundary layer thickness delta as a function of x, where x is measured from the leading edge. Okay, and the place where the transition happens to turbulent or starts to transition will be defined as xc. So for a flat plate, and I'm dealing with laminar flow, so let's deal with steady state, laminar and incompressible flow. For such a flow, dp dx is 0. In this case, for a flat plate, I should say. Flow over a flat plate happens without any pressure gradient, so dp dx is 0. So the governing equations become just the continuity du dx plus dv dy is 0, and the x momentum, which is u du dx plus v du dy, is nu times d2u dy square. If I also assume constant fluid properties, then so that constant fluid properties would mean that they do not depend on temperature or concentration, then the rather the hydrodynamic equations become independent of the temperature or the concentration field. So I can first solve this equation or these equations and then use the predictions from here and put them into the energy equation or the species conservation equation. Now, I mentioned one thing in the last class or maybe two lectures ago. I said something about an order of magnitude analysis of that is a way of how to solve this set of equations. So you may recall that I said if you look at continuity alone, so for flow over a flat plate, I know that I should actually also show. This is stupid of me not to show it here, but we mean what I meant was that there is a flow coming in at some velocity u infinity. So for flow over a flat plate, the u x component of velocity, which is u, scales as u infinity. X scale dx will scale as x, so that is the scaling law. And v, which is an unknown, and y scales at delta, where delta is the height of the boundary layer across which it changes. So these are the characteristic scales. So v basically, I mentioned in one of the classes that v will scale as delta by x into u infinity. And so v would be much smaller as compared to u infinity, and that is the reason we do not have a d2u dy squared term in the momentum equation, or the d2u dx squared term in the momentum equation. D2u dy squared is anywhere there. Okay, if you look at the momentum equation, I can do a similar scaling here for the momentum equation now. So if you look at scaling here, u scales as u infinity, du dx will scale as u infinity by x, v scales as we said delta by x into u infinity, u scales as u infinity, and this y scales at delta. So that is the left hand side, and the right hand side will scale as nu times u infinity by delta square. So this left hand side in a nutshell scales as u infinity square by x. The right hand side scales as nu u infinity by delta square, which means if the two have to be the same, because you're writing an equation, so it must be that the terms are comparable. So if the two terms are comparable, clearly delta will have to scale as nu what nu x by u infinity square root, right? Meter square per second. This becomes per second, so this cancels. Yeah, so that delta should scale as square root nu x by u infinity, and that's actually quite a powerful result because delta actually scales as some constant times this number. But just by order of magnitude analysis, we can prove that delta would have some scaling of this type. Now what Blasius did was he used this idea. So the solution that I'm not going to show you completely, but just discuss in a very shallow manner. Blasius used this idea and he derived what is called as a similarity solution for the problem. And the similarity solution was derived by getting rid of the continuity equation first. So he used, because you're dealing with incompressible flows, so he used the concept of the stream function. So I can write u as d psi dy and v as minus d psi dx, where psi becomes a stream function which ensures that my continuity equation is always satisfied. So using this and a similarity variable, which is which we will write as eta, which was written as y by some level of delta. So y by maybe some delta, and delta we derived in this form here. So it becomes y by u infinity by square root of, or rather square root of u infinity by nu x. So Blasis defined this as a similarity variable, which he said will be the independent variable for the solution. So instead of y and x being independent variables, eta became an independent variable. And the idea that he was trying to do or follow was, he was trying to write u by u infinity in the form of phi of y by delta, where y by delta is, as I said, is eta, so phi of eta. So he was trying to derive a solution for the velocity profile only in terms of, or the non-dimensional velocity profile only in terms of this variable eta. So to do this, what he did was, he said, if you say take a function of f of eta, which is related to stream function. So if you non-dimensionalize the stream function in this fashion, psi by u infinity square root of nu x by u infinity. So if you take psi in this form as a function of eta, then doing a little bit of calculus, which I'm not showing here, which I will maybe upload separately as my handwritten notes. So doing a little bit of calculus, you can show that the momentum equation now, which is here, the momentum equation can be converted into, even though the momentum equation is a partial differential equation, this momentum equation can be converted into a third order nonlinear ordinary differential equation. So using these, and I'm jumping these steps now, the momentum equation gets converted into a third order nonlinear ordinary differential equation. And the ODE that he derived looks something like this. So this becomes 2 times d3f d eta cube plus f times d2f d eta square is 0. So that was the ODE that he derived out of this momentum equation. And the boundary conditions for this ODE, because it's a third order ODE, so you need 3 boundary conditions. So he used the hydrodynamic boundary conditions and converted them into the function f. So for instance, u at x comma 0 is 0. And so he proved that this corresponds to df d eta at eta equal to 0 to be 0. Don't worry about how we get to df d eta. I will show you in the notes that I upload. Then he said v at x comma 0 is also 0, the y component, which comes out to be f of 0 is 0. That is the second boundary condition. And finally, the third boundary condition was that the velocity, if you go very far away in the y direction, right? If you go far away into the free stream, this should become equal to u infinity. And so df d eta, when eta goes to infinity, was 1. Now, this is the nonlinear ODE with these 3 boundary conditions. The typical, or the most convenient way, I would say, of solving this ODE with these boundary conditions is to do it numerically. And we have all done that. In fact, if some of you end up, as I keep saying, if you end up pursuing a master's or a PhD in fluid mechanics, you will actually have to solve this at some point on your own, numerically. So we have all done this. What you would typically get is that by numerical integration, when you solve this equation, the value of y at which u by u infinity becomes 0.99, which corresponds to delta, y equal to delta. This typically happens at eta of about 5. So that corresponds to y equal to delta, the boundary layer thickness in laminar flow. And so we can write that delta would be 5 times square root nu x, it's nu, by u infinity, which can also be written as 5 times x by square root of rex. So the boundary layer thickness clearly increases, increases with x, increases with x, or other, yeah, it increases with x, but delta will decrease with increasing velocity because it goes as 1 by square root of rex. So if the in laminar flow, if the distance as you go far away, the boundary layer becomes thicker, but delta decreases if the velocity, free stream velocity, increases. Using this solution and a little bit more about f, which I'm not showing here, the skin friction coefficient, which is defined as a wall shear stress by half rho u infinity square, this comes out to be 0.664 by square root of rex. And you may have probably done this in fluid mechanics, but I was reading just a few comments today in the mid-semester feedback. It seems like boundary layers was not covered, but I'm not sure whether this was also ignored. This is an important aspect. So you may have seen the skin friction coefficient as given by this equation, but it comes through the Blase solution. Now, the implication here is that as you go, as the Reynolds number increases, the skin friction coefficient at a given location will actually decrease, and it's highest, I would say, at the leading edge or near the leading edge where the plate just starts. Similar to the momentum equation, now once the velocity profile has been obtained, the temperature profile can also be obtained by non-dimensionalizing temperature. So we can write T star as using the same convention that we have followed in the last lecture. So this is the non-dimensional temperature. And so what we also do is, even though temperature should be a function of both x and y, we try and write T star as a function of eta, the similarity variable. So T star, we try and derive T star as a function of eta only. And in doing so, the we get a second order ODE for temperature. We now get d2 dt star d eta square plus Prandtl by 2 f times dt star d eta to be 0. That becomes the second order ODE to be solved for uh, temperature, knowing, or in which case f is known. F is already calculated from the momentum equation or the solution of the momentum equation. So in this case, the boundary conditions are, you need two boundary conditions. First will be T star at eta 0 will be 0 because T is equal to T, or T is equal to Ts at y 0, and so eta becomes 0 there. The second boundary condition will be the free stream condition. So T star when eta goes to infinity will be 1. So very far away in the free stream, the temperature should be T infinity. And so the T star value should become equal to 1. Now, for reasons of brevity, I don't want to go into details here, but for reasons I cannot explain here, but for Prandtl number greater than equal to zero point 0.6, the slope dt star d eta at eta equal to 0 comes out to be 0.332 times Prandtl to the power 1/3, which is basically the solution of this equation. So once you solve this equation, you take the derivative, and for Prandtl number greater than 0.6, it has been found that it comes out to be with this coefficient. And also using the fact that Nusselt number is, which is hx into x by k, which is also the non-dimensional temperature gradient. So dt star dy star at y star equal to 0. So combining the value that dt star d eta at eta 0 is something, and dt star dy star is similar to dt star d eta, h x comes out to be k times square root of nu x by u infinity. Sorry, the opposite in fact. U infinity by nu x into dt star d eta. And so the Nusselt number at any location x comes out to be 0.332 times square root of Reynolds number times Prandtl number to the power one third for flow over a flat plate, which is laminar and steady, and of course incompressible. So this is true for Prandtl, which is greater than zero point 0.6. And what it also would show you is that if you take the boundary layer thicknesses delta by delta t, which I mentioned in the last class, this is proved from this solution actually, that delta by delta t becomes Prandtl to the power one third. So the whole idea of doing this complicated exercise, and even doing it in a way that I have not explained many steps, was to actually show you in the big. When I started this segment, I said Nusselt number could be written as some coefficient into Reynolds number to the power m, Prandtl to the power n. So the whole idea of going through this task was to show you that it really works out this way, and this is one example where we can see that it is giving us the same correlation that I started, or that was the premise for my discussion today. Okay, so I'll stop it here. Thank you.